Hello students, welcome to today's lecture. In today's lecture, we just have a discussion on SSB-SC, that is a single sideband suppressed carrier technique. The learning objectives of today's lecture. First is introduction to the amplitude modulation, that is the SSB-SC technique, equations of SSB-SC, total power of SSB-SC, generation of SSB-SC. So first, we'll have a look on what is the amplitude modulation technique SSB. So SSB stands for single sideband suppressed carrier. Now, in case of double sideband suppressed carrier modulation technique, it is having a two sideband without a carrier, and the information present in both the sidebands are same. So there is no need to transmit both the sideband as they contain same information, and it will increase the total power consumption. So to avoid that, we go with the next type of technique that is called as a SSB. Here we are eliminating one sideband, either upper sideband or a lower sideband. Now the process of suppressing one of the sidebands along with the carrier and transmitting the signal sideband is called as a single sideband suppressed carrier system, or simply a SSB-SC. Or in simple way, most of the time it is called as a SSB, simple SSB, that is a single sideband suppressed carrier. So this is a process most widely used in modulation, in AM modulation technique. So let's have a look on its block diagram. So it consists of modulating signal, that is the information. That information along with the carrier is applied to the product modulator. Now carrier is a signal which is having a very high frequency used to carry the modulating signal, and these two signals are given to the product modulator. The product modulator is a type of modulator which is used or which is responsible for generating double sideband suppressed carrier. So output of product modulator is a double sideband suppressed carrier, which is having both sideband upper and lower, but do not consist of carrier, and then that particular signal is given to the band pass filter, which is having a cutoff frequency, and based on that cutoff frequency, it is either to the upper sideband or a lower sideband. We are getting SSB. Band pass filter is a filter which passes the signal in a desired range of frequency. So here we are selecting the range of frequency, or the cutoff frequency is selected as either the upper sideband frequency or a lower sideband frequency, and based on the choice of bandpass filter, we are getting SSB-SC. It can be either or, either upper sideband or a lower sideband. Then let's have a look on the equation of SSB. The modulating signal is generally given by Vm is equals to Vm cos omega nt, where the small Vm indicates the peak value of modulating signal. Omega m represents the modulating signal frequency given in a radian mode. Carrier signal is represented as Vc is equals to Vc cos omega c t, where omega c is a frequency of a carrier signal and Vc is the amplitude of a carrier signal. So we are having a modulating signal with a frequency of omega m. We are having carrier signal with a frequency of omega c. Now these two signals are given to the product modulator. Product modulator will simply do multiplication or generate the product of modulating signal with the carrier. So it is given by Vm into Vc, and the output is nothing but the DSB-SC, which is given by m of t cos omega mt into cos omega ct. Omega m is a frequency of a modulating signal, omega ct is a frequency of a carrier signal, and this m of t represents the input signal, that is the modulating signal voltage. Now, how to represent the AM signal in a frequency domain? So the generalized representation of an AM signal is given by Vc1 plus m sine omega mt sine omega ct, where this m is nothing but the modulation index. Omega m represents the frequency of a modulating signal, and omega c represents the frequency of a carrier signal. Now the modulation index of a signal, of a AM signal, is nothing but the ratio of Vm by Vc, where Vm is the modulation signal voltage and Vc is the carrier signal voltage. So this is a general representation of a AM signal. Now we just do little bit modification of this equation. Now here we just first open up the bracket. So Vc into 1 into sine omega ct is the first term. Vc into m sine omega mt into sine omega ct turns out to be the second term. Now this m into Vc is nothing but Vm. By the basic definition of modulation index, that is M is equals to Vm by Vc. So this MVC is replaced by Vm. Now again, we are using one more trigonometric identity, that is sin A into sin B. So sin A into sin B is nothing but half cos A plus B minus cos A minus B. So here A is nothing but the higher frequency, that is the frequency of a carrier, and B is nothing but the frequency of a modulating signal. Now performing this particular or applying this particular trigonometric identity to the sine omega mt and sine omega ct, we got this modified equation. So we see sine omega ct remains as it is. For this, we are getting Vm by 2. Vm half is 2 cos omega c plus omega m minus omega by 2 cos omega c minus omega m. So this one is the second term. So this is a general representation of AM signal in a frequency domain mode where we are having three terms. So this is the carrier, upper sideband and the lower sideband. Now the modulated carrier has two signals at different frequency called as the sideband frequencies or sidebands. They occur above and below the carrier frequency. So the frequency which occurs above the sideband, above the carrier, is called as the upper sideband, represented by FUSB. Its frequency is FC plus FM. And the frequency which is lower than the carrier is given by FLSB, that is the lower sideband frequency, given by FC minus FM. Now this is a frequency which is in the normal format, but the frequency which is available with us is in the radian form, that is the omega c and omega m. So omega c is nothing but 2 pi fc and omega m is nothing but 2 pi fm. Now putting these values in the equation of AM, we got Vc sin omega c. Omega c is replaced by 2 pi fc and omega m is replaced by 2 pi fm. 2 pi is taken common, so we are having fc plus fm. Similarly over here, so this is the equation. Now this particular signal is applied to a band pass filter. So band pass filter is having cutoff frequency either to upper sideband, that is to fc plus fm, or to the lower sideband, that is fc minus fm, and based on that it will generate two signals. First one is the upper sideband, where the frequency is where the center frequency is fc plus fm, and the second one is a lower sideband where the frequency is fc minus fm. So this is the output of SSB, either upper sideband or a lower sideband, based on the choice of band pass filter used. Now regarding the spectrum, so the spectrum consists of upper sideband or lower sideband. So here the carrier and the lower sideband portion is suppressed. So we have not indicated it, and therefore it is represented in the dotted line, but only upper sideband is transmitted with a center frequency of fc plus fm. So this particular is the frequency spectrum for the upper sideband frequency. Now regarding the bandwidth, so the bandwidth is nothing but the difference between the higher frequency and the lower frequency. So here, as the lower and the carrier portion is suppressed, so we are having only upper sideband. So for finding out upper sideband, upper frequency, we consider fc plus fm, but for the lower, as lower frequency is not there, we just consider the origin or the center. So the center in this case is fc. So therefore, it is written as fc plus fm minus fc. So fc plus fm minus fc get cancelled. We are having only fm. So if you compare the frequencies of DSB-FC and DSB-SC, the frequency or the bandwidth requirement of SSB-SC is less. It is having only FM, whereas in case of DSB-FC and DSB-SC, that is twice FM. Now, regarding the calculations of the total power of SSB, so as SSB consists of only upper sideband or lower sideband, so we are going to find out total power by considering the power of either upper sideband or the lower sideband. The power is given as power of upper sideband or a power of a lower sideband. The generalized representation of a power is nothing but V square by R, where V indicates the voltage, but this voltage is in RMS voltage, and the voltage which is available with us is a peak-to-peak voltage. So we need to make the conversion. So the formula for conversion is Vrms is equals to V peak-to-peak divided by root 2. And this VUSB or the voltage is nothing but MVC by 2. So this is a voltage of upper sideband. And putting this equation, we just put VUSB as MVC by 2 in the first, and then in the formula for power, after that we got V PUSB is equals to M square V square divided by 8R. So this is what I'm going to explain you. So what we did, we are having VUSB as MVC by 2. So what is my VUSB become? So VUSB is equals to MVC by 2 divided by root 2. Putting this in this equation and then we put it in the formula for a power. So for putting it in the formula, it will become whole square divided by R. So it will become M square BC square, 2 square is 4 and root 2 square is 2. It turns out to be 8. So that is how we got the formula for the upper sideband power, which is equals to M square BC square by 8R. Now one more thing, the power of upper sideband and lower sideband both are same. So therefore we are getting both as a same. And one more thing, we are replacing this VC square by R as the carrier power. The carrier power is nothing but VC square divided by twice R. So by putting that here, we got PSSB as M square by 4 into PC, and therefore the total power of SSB-SC signal is given by PC M square by 4, where this M is the modulation index, which is given by VM by VC. Now, regarding the generation of SSB, so there are various techniques used for generation of SSB. First one is the filter method, phase shift method, and the third method. And among all these three methods, in today's lecture, we are going to have a look on the first technique, that is the filter method. Now, this filter technique is also called as a frequency discrimination method because here we are changing the frequencies of the signal. So therefore, this is the first technique, filter method. Here we are using filters for the generation of DSB, for the generation of SSB. So first thing is for filter method, first we are generating DSB-SC and the output of DSB-SC signal is given to the bandpass filter, which will ultimately results in a SSB-SC. So this is a block diagram. So we are having a crystal oscillator, which is nothing but the carrier generator. Its output is given to the buffer and via buffer it is given to the balance modulator. Second input to the balance modulator is a modulating signal or the information which is passed with the through a audio amplifier, which will amplify the signal, and that amplified signal is given to the balance modulator. The balance modulator is responsible for generating DSB-SC. So it will generate a DSB-SC signal or it will generate two sidebands. Now the output of this balance modulator, that is the DSB-SC, is given to the bandpass filter. This bandpass filter is nothing but a sideband suppression filter, and based on the cutoff frequency of this particular bandpass filter, it will generate either upper sideband or a lower sideband. That is nothing but the SSB-SC signal. So this is the first part where we are generating SSB-SC signal. Now the strength of this SSB-SC signal is very low and we need to boost that signal. So for that, the second portion is there, that is the up conversion. So for up conversion, the SSB-SC signal is multiplied with the high frequency generated by the crystal oscillator. These two signals are mixed together and it will generate a up converted SSB signal, and then it is passed to the linear amplifier, and through linear amplifier we are getting SSB output. So this is how the filter method is used for generating SSB-SC. So first SSB-SC signal is generated and then the second part is the up conversion where we are boosting the signal, we are increasing the frequency and the amplitude of the SSB-SC signal. Now regarding the advantages and disadvantages. So first we'll have a look on the advantages of using filter method. So filter method is having various advantages. The first is this method gives the adequate sideband suppression. So as we're using a filter, so the filters are designed so that it will generate a desired value of sideband. The sideband, so as the filters are used, if any portion of carrier is present at the output of DSB-SC or in the balance modulator, if any carrier is present, so if you apply that signal to the band pass filter, it will also eliminate that portion. Then bandwidth is sufficiently flat and wide. This method is simpler as compared to the other techniques. Disadvantages. So the major disadvantage of using filter method is that the low audio frequency cannot be used as the filter becomes bulky due to inability of the system to generate SSB at high radio frequency. The upconversion portion is there. So the output which is generated in this technique is not of high frequency value. So we need to use that upconversion. So that extra portion is added. And here we are using two expensive filters are used for both sides. So for upper sideband we are using one filter, and for lower sideband we are using another filter. So this will make the system very expensive. So switching of sideband is not possible. See here we cannot switch in between upper sideband and lower sideband. So once that filter is designed for upper sideband, it will generate only upper sideband. Once it is selected for lower sideband, so it will generate only lower sideband. So here the switching of sideband is not possible. You will get either upper sideband or a lower sideband. And major drawback, we cannot generate SSB-SC at any frequencies. Then what are the advantages of SSB-SC? So the bandwidth and the spectrum occupied by SSB is less, that is only FM. If you compare it with AM and DSB-SC, that is for them, it is twice FM. Transmission of more number of signal is allowed in case of SSB. Power is saved because here we are transferring either upper or lower sideband. So the power requirement of SSB is very less compared to uh, that of DSB, FC and SC. So as its power is saved, its efficiency is also high. High power signal can be transmitted. Less amount of noise is present in case of SSB. Disadvantages: the generation and detection of SSB wave is very complex because we are suppressing the carrier, and after that we are suppressing the sideband. So it will make the system very complicated for designing. The quality of signals is affected unless the SSB transmitter and receiver have an excellent frequency stability. So if the transmitter and receiver which are used for SSB is not having a good frequency stability, it is going to affect the nature of SSB signal. And what are the applications? So it is basically used for power saving and the low bandwidth requirement. So the applications where we need less power and low bandwidth, so for that applications we go with the SSB. In land, air, and maritime mobile communication, it is used in the point-to-point communication, in radio communication, in television and telemetry and radar communication. It's also used in the military communications such as armature radios and etc. But the basic need is the system where we need low bandwidth and a power saving. So for that system only we go with the SSB. So as it requires very less bandwidth, that is of only FM, and power saving is there because here we are transferring only one sideband. So the applications where the power saving and low bandwidth is needed, we go with the SSB. So that is all about the SSB. Thank you so much for listening to my lecture.